I think it might be here.
You can check first.
It was on Indico.
Was
I put
it
it
on
on Indico, but you have no access on the Indico? On the Indico program.
Let's load it.
Yeah.
So take the PDF because...
Which one?
Do you have audio here?
Audio. Yes.
So can we try both? It's EHC presentations. There is one which is PPT and one...
Why it's PPDF?
So this is a PDF?
Let me see. I think
It's
so.
on.
Yeah, PDF.
Yeah, we've seen it on the
So
big
take the
screen.
PDF, it will be easier. Can we try also the
Can we have a
PPT?
look at the setting?
This is the PPT. Yeah.
Just below.
You can
Okay.
present from this laptop.
Click it. You want to have a look at?
Each one over
No, it
there.
does not work. Do you see? So forget about the
Okay.
PPT, we take the PDF.
Okay. So
You know,
we
PPT, there is always some problems of compatibility. PDF should be okay. Yeah, PDF is
PDF. Okay. Let's say I copy it to this computer. Okay.
We should be able to see the Zoom
So it's
people,
here?
but we haven't got them yet.
Okay.
The second
Yeah.
bus has arrived.
perfect.
Yeah.
So
Okay.
we're having a
And
mild
so okay. Yeah. So this is on the desktop. On the
Yes.
Yeah. Okay.
starting in, and I've left my watch somewhere. Yes. I'm sitting there. Maybe we can move one chair. Oh, I'll move my luggage, okay? You could sit on the luggage chair and set up. Okay. And you have the temple chime, which I can use. How do I get it full screen?
This one.
Oh,
Okay.
okay.
Yeah. And you use this to go back. Yeah. And this is the laser. You use this one to get this laser
Okay.
and this forward backward. Yeah.
Okay.
Yeah. Okay.
Are you ready? Good day. Good day to everyone here. And thank you for arriving perfectly on time. This is a session that is constrained by 2 bus trips. My name is Igor Gledhill. I'm Secretary of Working Group 21 in IUPAP. I will function as chair, but the symposium is going to be introduced by other people. Just a few notes. This Intercommission Symposium for Physics Research for a Sustainable Planet has been very kindly hosted by the Chinese Physical Society, and it is an IUPAP symposium, and the intention will be described by Professor Pietro Ubertini in a few minutes. We won't provide long introductions to the speakers, but there is a booklet on the CERN site, which we will put on the screen occasionally. There is a broadcast on Cowshare and YouTube, but not all talks will be broadcast. So may I invite Professor Xiaoyan Xin to come and welcome you. Thank you.
Okay, so first of all, I would like to welcome our friends from the IUPAP to China, and then also welcome all of you to join this intercommission symposium to be jointly hosted by IUPAP and CPS. And actually, lots of people have done tremendous work to make this happen, like Ego just mentioned, and from the Petra, and also from Nisaya, and from Ego, and from the IUPAP side, and also from Li Lu, from the CPS side. So they have done lots of work to make this happen. And we know that we are facing the great challenges both in many aspects like the climate change and also in the sustainability of the energy and so on. And so here we just stay here and meet here to try to share our experience and share our information and ideas, and also to discuss how to contribute as a physicist to contribute to the sustainable development for a better future. So I wish you will enjoy this meeting, and also I wish you also enjoy this very beautiful island here in Haikou, and thank you very much for your coming.
Sure. I cannot say how much we are grateful for this. Professor Michel Spiro, President.
Thank you very much, Professor Xiaoyan Chen. We are very sensitive to what you said, and this is just in line with our priorities. I recall them because it's always useful to have them in mind. First, what is IUPAP? IUPAP is the only global organization in physics. Its mission is to foster the development of physics, the global participation to physics, the collaborations in physics, and to foster applications of physics which could be of some help for humanity. Typically, this is trying to develop what we call regenerative development, so global equitable development on a healthy and lively planet. So this workshop is exactly in line, this symposium is exactly in line with the mission of IUPAP. I want to thank the two main organizers, Igle Gledil and Pietro Umbertini, for the job they did and for the opportunity they give us to illustrate what we are doing in this direction. Thank you.
The intention of this symposium will be summarized by Professor Pietro Ubertini. Now, this symposium was actually suggested by him as a means of bringing commissions together.
Yeah, thank you. Actually, it's an initiative of Commission 19. After we made a report 3 years ago on the astrophysical result, we realized that it was not enough. So, in particular, Andrea Bucket, that was the vice chair or the secretary, he was very supportive of this idea. And now we are here, I hope, for a great and exciting symposium. I want to thank again everybody, all the speakers and participants at this. This is the Intercommission IUPAP Symposium that is co-organized, as we said, already by Commission 19 in astrophysics and Working Group 21, quite a young working group that is Physics for Climate, Change Action and Sustainable Development, co-chaired by Nitalia Chetty and magnificently coordinated by Igor Gedil, that did most of the job. I want to convey a special thank to Professor Xiaoyan Shen, that is our host, to Michel Spiro, that is our president, and has enthusiastically promoted the idea of this symposium a few years ago in Trento at one of the General Assembly of IUPAP, and in particular to Giorgio Parisi, that is Nobel laureate 2021, that has kindly agreed to open the works, and he is online. And finally, welcome to all the participants. I should say what is this symposium, what is it intended for? You will discover in 2 minutes at the end of my speech. As Giorgio recently said, physicists are living in the future. And IUPAP is the house of all physicists, so we are all living in the future. This is true in general. Think about Einstein, that people was barely understanding the gravity. He said the gravity do not exist. And then we need hundreds of years to permeate the information to the general people. We have an incredible harvest of discoveries that were partially depicted yesterday by the 3 Nobel laureates in the field of gravitational waves, with the first detection in 2015, and the astrophysical kilonova detection 2 years later, generated by the first neutron star coalescence associated to a gamma ray burst. So for the first time, we had signals in 2 completely different areas, light, that are gamma ray bursts, and gravitational wave, 2 completely different ways to look at the universe. And the 2 signals arrived at 1.7 seconds. The gravitational wave signal arrived before, and almost 2 seconds later, we got this gamma ray burst detected by Fermi and integral satellites. And this is weird, because after traveling 130 million in the universe, these 2 signals were tiling each other by 1.7 seconds. And gravitational wave arrived first, and second gamma ray burst. So the question is, are these 2 speeds different? Of course, probably not. But anyway, this one measurement permits us to give an evidence that gravitational wave and light travel at the same speed within an uncertainty of 10 to the minus 15. So we know that if they are not identical, they are almost identical. And this is another challenge to understand. Of course, we heard yesterday about neutrino, cosmic rays, the intriguing far-radio bursts. We don't know what they are. We have bursts of milliseconds coming from each part of the universe time to time. And because they last only 1 millisecond or less, it's difficult to understand who's emitting that. This is in the radio domain. And also we are still chasing the first star that should be only hydrogen, but we never saw the first star. We saw the sun and the nephew of the first star. Artificial intelligence is a daily reality with opportunities and challenges for human evolution, as well as new energy sources. Climate change and geohazard, nuclear weapons production, control and treat are more and more difficult to keep at a reasonable level. And this is the conclusion of my thinking. In this IUPAP, and I will take freedom to mention COSPA, the Committee on Space Research, that is aligned in the same direction of IUPAP, has a paramount role in maintaining an open bridge between people in this difficult moment. Difficult moment due to international stresses, while regional wars are used instead of diplomacy to solve conflicts that are unfortunately becoming a reality at the global level. You see of a new war started day by day. So I'll finish here, also because I'm very curious to hear what our speaker will say, in particular Giorgio that will start. And I hope that in the next 2 days we will have an important and interesting symposium that is a physics research for a sustainable planet. This is the intention of the symposium. Have all the physicists thinking how to have a sustainable planet in all means, not only for the physics research, but all the themes that we will attack in this 2-half day. Thanks, and have a productive conference.
Thank you. This is a collaboration, and the collaboration is between essentially C19 and Working Group 21, Physics for Climate Change Action and Sustainable Development. So here is Professor Nithya Chetty, chair of that working group.
Thank you very much, Igor. You've done all of the heavy lifting in organizing this symposium. Thank you so much for that. Colleagues, very briefly about the Working Group 21. This was established a year ago, and it was really due to confluence of many different developments. Of course, you know of the 21 Nobel Prize in Physics, and soon we will be hearing from Professor Parisi. He's part of this symposium, but it was also in 22 when Michel Spiro led the establishment of the International Year of Basic Science for Sustainable Development, and both Igor Gledil and myself got together and made a proposal to the IUPAP Council that we establish this working group, and last year at the General Assembly this was established. Since then, of course, we've had the International Decade for Sciences for Sustainable Development that's been established. And once again, thanks to Michel for his sterling efforts in this regard, and now we're super excited about the new development around Earth-Humanity Coalition. So all of this, these are multiple endeavors, but through the Working Group 21, we hope very much that we will be able to coordinate these different initiatives and see Working Group 21 as a conduit within which IUPAP can get involved. So we were very clear early on not to duplicate other efforts, for example, through the IPCC. So the key mandate for Working Group 21 is to identify, but also to promote new ideas along the lines of what physics can contribute to this rather multidisciplinary endeavor. And so the work of commissions, working groups, physical societies, other unions around the world are extremely important in the work that we're doing within the working group. So one major action item for us is to organize a major conference, a major international conference. We intend for this to happen in the year 27. The call will go out sometime soon. So in some ways, this symposium is meant to be a forerunner for what that major conference, 3-day long conference will entail. Now, sustainability is obviously a very wide range of topics, covers practically all subdisciplines of physics, so there are ample opportunity for all commissions to get involved in this conversation, and therefore it was absolutely critical that when Pietro Umbertini came forth through C19 and said we need to host such a intercommission symposium on the topics around climate science or sustainability. We have many different ways of saying the same thing, really. We all care about the same things, about the sustainability of our planet and more equitable ways in which human beings can coexist on this planet. So this is really now the beginnings of in getting the commissions together, Pietro, and I hope that you will continue to play this role as being a key coordinating point for us within Working Group 21. You've already made those connections with the other commissions. So with that then, colleagues, I would like to wish you all a very successful symposium. I'm certainly looking forward to the discussions, and once again, Eagle, a very big thanks to you for all of your organizational efforts.
Thank you very much indeed. I'm going to move to a slightly different presentation for a reason that I will explain in a moment. And that, I understand more Chinese than I thought I did. So I have realized that this program is not available to everyone who doesn't have access to the General Assembly site. So it is on the Indico site, and it contains the biographies. It contains the biographies of our speakers because it is a case of, if I give the full biography, then the bus will be lost. For want of the bus, the banquet will be lost. And we can't allow this. So I will make sure that this shows every now and then. I'm now going to introduce Professor Michel Spiro again, because we are now in, I need some help. I need to go to Professor Spiro's slides. Yes, there. I'm also going to explain that, and your name is? Yi Chandu is an integral part of this symposium. He is the one who actually gets things going. Professor Spiro, you have two talks.
Thank you again. I hope that you see that with this symposium, IUPAP contributes to, with the diversity in the room, people coming from everywhere, IUPAP contributes to a better global understanding through physics, which I think is very important. So I will try to cover what happened recently, which is the move from the International Year of Basic Sciences for Sustainable Development in 22 to 23 to the International Decade of all sciences and all knowledge for sustainable development 2024-2033, both proclaimed by the UN General Assembly and under the auspices of UNESCO. So briefly, I will recall what happened with the International Year of Basic Sciences for Sustainable Development. So it was proclaimed by the United Nations General Assembly end of 2021, opening ceremony in 2022, July 8th. So due to the late proclamation and to the late opening ceremony, in fact, this was the international year spanned over 2022 and 2023. The resolutions were brought up by these countries, but it was a consensus with all countries, all members of the United Nations General Assembly. The rationale is given in a very nice video, but I have no time to show it. But if you go to Indico and you upload the PowerPoint, you will find it. It's a 1-minute video. But I summarize it here with few sentences. Why basic sciences are important for sustainable development? Because curiosity-driven sciences, what I call basic is curiosity-driven sciences, construct the pool of knowledge which future generations will use for their development. And as you know, there is a tendency to look for applications now. Governments are interested in the economy and in the innovation more than in curiosity-driven discovery. But this is short-term approach, and they should always have in mind that the long-term approach, the sustainability, means to fund curiosity-driven sciences. Besides filling the pool of knowledge for future generations, they also contribute to re-enchant our world and make it worth to be sustainable. I mean the history of the universe, Big Bang, the particle physics, the Higgs boson, all this stimulate our imagination. So basic sciences explore in some sense what is at the heart of the universe. So, however, among among the conclusions of this, the outcome of this international year, we had to realize that although essential, basic sciences are not enough for sustainability. You need to embark all sciences, basic and applied, natural and social sciences, even humanities, and even all knowledge in the society, knowledge, indigenous knowledge. You need to embark all that and to co-construct scientists and the society, co-design, co-construct solutions, so impact-oriented solutions for sustainability. So all sciences and all knowledge are needed for equitable well-being on a healthy planet. This is what I called equitable development on a healthy planet, what I called regenerative development. I prefer the word regenerative than sustainable development because there is a bit of a contradiction. We will see that in a specific talk later on between sustainability and development. While regenerative, taking care of people, improving in an equal way their well-being, redefining what we mean by well-being, and this has to be defined according to the territories, and asking for healthy territories, lively planet. This is what we call regenerative development. This is perfectly in line what I said. So this is exactly the goal of the Earth Humanity Coalition, which is inside the International Decade of Sciences for Sustainable Development, which was proclaimed by the United Nations General Assembly in August last year, 2023. Explicitly in the resolution, it is mentioned that we should embark all sciences and all knowledge, including indigenous. So the Earth Humanity Coalition has this ambition of pursuing what we call regenerative development, global equity, equitable development for a healthy planet. Our Earth Humanity Coalition is a coalition of now about 55 academic and non-academic. Again, we want to have sciences and non-academic organizations. The idea is to try to foster transformative actions, which means co-constructed actions together with the scientists, with the society, at multiple scales. So these are territorial research and knowledge developments at multiple scales, going from local to global, so which means from villages, transformative actions at the level of villages, of provinces, of countries, of group of countries, and globally speaking. The idea is to promote the activity of transdisciplinary hubs, so scientists together with society in centers at different scales. It's a new way to do research. Instead of doing research in a research laboratory in an ivory tower, the idea is to have research centers together with people, stakeholders coming from the society. And by that way, looking for impact targeted activities rather than only publishing. We are partnering, obviously, with UNESCO, since the International Decade is under the auspices of UNESCO. We are also partnering with ISC, because ISC has the same goal, but the approach is more top-down, so acting at the level of the United Nations, a multilateral system, at the level of the funding agencies, so that they start to fund this kind of initiatives which are co-constructed between the society and the scientists. So the ambitions are clearly to integrate knowledge and science, to collaborate across all sciences, I did that, I said that, but also to include the society with the traditional and indigenous knowledge, with a focus on the sustainability driven by equity and well-being for all on healthy territories, regenerative development. So this is reimagining the role of science, I told you that, and with science which is co-constructed and impact-oriented. With that, we want to bridge divides. So the idea is to have a collaboration network of all these transdisciplinary centers, maybe, hopefully at the end of the decade, thousands of centers like that in villages all over the world and in provinces, in countries, and globally speaking. We must have an equitable knowledge creation. If you create knowledge together, the society and the scientists, the society should not be considered as data providers for the scientists. It is co-creation, which means that you have to respect the input of the society and to try to evaluate the input of the society and the input of the scientists. The hope is that we will have a strategic outcome in 2033, and that the sciences and society will be much better equipped to master these challenges in front of us. So, concretely speaking, what we want to do is first to make an inventory of what is already existing, about 100 transdisciplinary or co-constructed hubs all over the world, which are funded by the Belmont Forum, which is a club of funding agencies worldwide, funding this new way of doing science. So we are establishing a partnership with the Belmont Forum and trying to establish a network. For instance, we will promote a collaboration between these hubs. And the first collaboration could be to use an open platform. At CERN, we call it Zenodo, which was used for the Higgs boson discovery to interconnect the data and the IT infrastructure of thousands of laboratories worldwide for the Higgs boson discovery and Higgs boson study at the CERN LHC. So we want to do a little bit the same with the transdisciplinary hubs to interconnect them so that they share their data, they share their papers on this Zenodo platform, they share their narratives, they share their best practices. Zenodo was already intensively used for the COVID-19, and I think it should be used now for sustainability. So this is a concrete action, and maybe later on we could try to put the IT infrastructures together, and even citizens could bring their own PC in the game so that we have an overall super computing capacity which is distributed all over the world, which is both an IT infrastructure and a collaborative structure. This means extending the spirit of big science, I mentioned the LHC at CERN, to the intercultural bridges and peace. We have also to define what we mean by well-being. Well-being is not necessarily meaning to target the US way of life. We have to invent, and this has to be defined on each territory, what we call well-being. So we have to co-construct this target of well-being with science and wisdom from everywhere. And we have to formulate critical questions for equitable well-being. It must be sustainable. So as you see, we have really strategic goals for 2033 for sustainable development with this agenda, which is very ambitious. And we have to start to approach the funding agencies so that they reframe their research and funding scheme. And as I said, we have to establish a co-designed organizational structure to support this Earth Humanity Coalition. To do that, we are establishing 3 working groups with our partners. One on defining better than I said, the strategy. By the way, Praval Shastri, who is maybe here, is chair of this working group. We have to define the programming of activities in the next year and in the next 5 years and in the next 10 years. And we have to also establish a legal entity for this Earth Humanity Coalition. For the time being, this Earth Humanity Coalition is hosted by IUPAP, as it was for the International Year of Basic Sciences for Sustainable Development. But the hope is that by 2025, we will have either a legal entity on some other organization hosting, maybe IUPAP again, but or some other organization hosting the Earth Humanity Coalition. A good candidate could be the Club of Rome, for those who heard about the Club of Rome. So you see, you see the timing for the Earth Humanity Coalition. We are in a phase of activation, which will be, and we will pursue then a phase of expansion and a phase of consolidation. The organizations is now, it is being revisited by the third working group, but basically for the moment it is a steering committee. I will show you the members of the steering committee, a programming board, the activities. I hope very much that what you have in mind with working group 21, this large conference could be part of the activity. So the programming board will have to interact with you to see if there is a good understanding between you and the Earth Humanity Coalition. We need a high-level support committee, so Nobel laureates, to attract funds from sponsors. We have a secretariat, but we have to develop it. And we have a general assembly of members. Sorry, 5 minutes? So I will go fast. The action plan for 2024 is done. I will skip all that because we have no time. And just tell you that we are clearly, with these 3 working groups, identifying the value added by this Earth Humanity Coalition. Clearly, we have a cooperative and open attitude and work practices. We are looking for a holistic knowledge integration, co-construct, co-design, global bottom-up network of transdisciplinary hubs. This I said that many times. Mobilizing infrastructures for sustainability at all scales. This is this worldwide grid I mentioned. Focus on equity, just futures, and planetary reconciliation at all territorial scales. And the ambition to get this translated into the funding, so a kind of science policy nexus and research and innovation agendas. So many events have happened and are happening now. And I will finish by mentioning where we are with the steering committee. It will increase from this number to probably 15 people. So there is Carlos Alvarez Pereira from the Secretary General of the Club of Rome, Spain. Leslie Green, also a member of the Club of Rome. Africa, Social Sciences, University of Cape Town. Carlos Alvarez Pereira is more an engineer. Stephen Hartman, UNESCO Most Bridges Coalition, Sweden. Nebojša Nešković, a physicist, but also the president of the World Academy of Art and Science, Serbia. So this shows clearly that we want to have an alliance between science and art. Marian Kanza, University of Science and Technology, Ghana. Prajval Shastri, you know her, she is now the chair of the Working Group 5 Women in Physics, astronomer, but also physicist, member of very connected to IUPAP, India. Luc Allemand, coordinator of this Earth Humanity Coalition. He was coordinator of the International League of Basic Sciences for Sustainable Development, France. And Raad Sharar, Bangladesh, program coordinator, the Club of Rome. We are missing Latin America, and we have to enlarge a little bit this. And the North America also. And I think that's all, Igor. Yeah, so I don't think that we have no time for questions, and we can, during the coffee break, you can approach me if you want to have more information. So let me now go to introduce a new speaker. So the speaker after me, he is well known, Giorgio Parisi. He is a friend of IUPAP. He was very much connected. He was and is very much connected to IUPAP. He was the Nobel Prize laureate in 2021 in physics. His affiliation is the University of Roma, Sapienza, University Sapienza. And the prize motivation for the awarding of the Nobel laureate was for the discovery of the interplay of disorder and fluctuations in physical systems from atomic to planetary scales. But basically, Giorgio Parisi embraced all aspects of physics. He knows everything about physics. And now sustainability. Parisi, the floor is yours.
Okay. Thank you very much. I'm very glad to be invited here to this very, very important meeting. And I apologize that it was impossible for me to come in presence, but because what people discussing here is extremely important. Now, in my talk, what I will try to concentrate is essentially what physicists can do for a sustainable planet. Of course, you know that there have been a lot of discussion these days with a wonderful Nobel Prize that have been given to Hopfield Hilton if what they were doing in physics, not physics. But I think that we are not to concentrate on names. I think that what is important, what physicists can do, and what physicists can do as in physics, but also generally speaking in society. Now, I think that there is a wide range of action that physicists can do, and which I will discuss later on, going from different viewpoints. And what is very important is that we are living, that is, must be clear, in a defining period of human history. I mean, we do not know whether the progress that we have seen so far will continue in any way, or whether it will suffer a collapse in this century. The Club of Rome 50 years ago, the book they wrote was prophetic, and now is quite clear to us that we are approaching a point of non-return. We hope that we can avoid it, but we have to work in a consistent way to avoid this problem. And now we see that various crises overlap and intertwine with each other. On one end, we have the progressive depletion of raw material, and on the other end, we have climate change that is beginning to produce effect because before everyone's eyes. Global warming is very important, and land consumption and pollution aggravate the crisis of the planet ecosystem. A large number of animal and plant species have become extinct forever. On the top of that, we have, as I will discuss later, we have the problem of trust in science. Trust in science is decreasing in some way, and that is something that we have to tackle, not only as physicists, but also on scientists. And also what is very important is that science go in the direction to increase the collaboration between different people, different countries, and also to sustain peace. Now, there are many things that we can do. One of the things that we can do is the physics, and we have to understand what happens now to our planet. I mean, it's not so easy to understand because there are many things that we are missing. For example, one thing that I was really impressed is by the fact that in some sense we really do not know exactly where the CO2 or carbon dioxide that we produce, where the CO2 goes. Now, we know the different production that we have. We know many things, but more or less, one thing that we have not under control is certainly the oceans. Now, if we exclude the oceans, we know that more or less half of the CO2 is not accounted by the other things. So this has to go into the oceans, but we do not fully understand the mechanism where CO2 go into the oceans. where and which part of the ocean it goes. And this is very complex things because it involves also the exchange of the water that may be CO2 rich at the surface with water that are in deep, which are not rich in CO2. So it's an exchange of CO2 for the surface to the deep of the oceans. And in order to understand these things, we need a program to monitor oceans, and this is a program that is going on, is increasing, and is extremely important. It is extremely important because as far as we do not know well this mechanism, this forbids us to do predictions on the future of this mechanism. Therefore, we do not know when, if this mechanism will stop in the future, it will be, or it will become more efficient in the future. And so this is one big thing that we do not understand for the future. And what other things that we have to understand that are very important is what happens the relations between the water of the ocean and the ice sheet, because it's clear that the presence, because the ice sheets sometimes are over the oceans and the water below is very important. Now the problem is the AMOC, the Atlantic Meridional Overturning Circulations. We started to have some evidence that have been slowed down in the last century, a very small one. However, it's something that is going to give some type of concern, because we know that in the past we had many events in which the AMOC stopped to circulate, and to stop it to be there or become very, very slow. And therefore, this is something that will be completely change, affect our climate. It's something that we have to understand. And of course, we have to, a very important thing that we have to do, that physicists are doing, is to improve remote sensing. There is a remote sensing exclusive, and every year we have a new satellite, a new instrument, and this is a very important thing to which physicists can certainly use. Now, the other problem that we have to do is to do predictions, the prediction for the future. We need the more accurate predictions. And one of the problems that we have in doing very accurate predictions that we have to control better what people call point may some kind of catastrophic event. And for this type of catastrophic event, it's very difficult to have a very precise prediction. For example, what we should be understood clearly that when an IPCF predicts that there is some intermediate scenario of reducing greenhouse emissions, the temperature could rise between 2 and 3 degrees. That this range is what can be estimated for current knowledge. But the current model that what is temperature arise more than maybe other phenomena maybe much the things that we add the system is something that is very difficult. One should be very to not know which that some new the claim which are valid in the short time at the time from use other action. It's not only a question of having an energy production system which is more efficient. For example, speaking, if you look to solar cell, because it's clear that increasing for 17% to 20% efficiency is very important, but we need a system that are very simple to implement, simple to construct. We need a system which polluting when in the sense that when you have to dismantle 20 years from now the solar panels that we are starting installing today, we need a system that will not be polluting 20 years from now. And also we think that we have to produce something which is less based on raw material, because raw material shortage is also something that is going into the direction of better sustainability. And of course, the fact that we need to decrease the pollution is something that is extremely important, because if high level of pollution would be a complete disaster. And also we have a problem that we need not only energy conservation, but we need energy saving. We have to understand which are the technology which are less important for that produce less, that help us to save energy, because a lot of our energy that we produce go in transportation, goes in heating and cooling the houses. So we have to understand better this type of technologies. Of course, it's quite older technology, but certainly we can do something that is improve them. Now, one point, however, that should be that physicists should, scientists in general should tackle is the problem of trust in science. Now, it's clearly that we have to make essential choice, for example, for climate change. But we know that science has been warning us for decades. The human behavior was setting the stage for a step rise in our planet temperature. This was done by the other two Nobel Prizes in 2021. We started to do these studies in the 70s, in the 80s. So it's 40 years that we know more or less with a relative accuracy that the temperatures were going to increase with catastrophic conference. However, it's clear that up to now, up to, let's say, a few years ago, but the response of the government of the population was very mild. And now the climate changing is beginning to affect people's life. There's beginning perhaps to more assertive reaction, but it's quite clear that we need to have a stronger measure. And now we know from COVID experience that it's not easy to take effective measure in time. And that is a real problem, and also is something that is a general problem, is that if the society has to use very strong countermeasure, this require trust in science. Now, we see that in some sense the trust in science have been decreased in some kind of recent years. And now we see that there are strong anti-scientific tendency in the society, and the prestige of science and the trust placed in it are rapidly declining. We have we can see for all the problems that we had with the Novax movement also before the COVID, and now during the COVID, we've seen the tragedies that happened to the people which were denying COVID. They refused to vaccinate because despite millions of deaths. Now, it's clear not easy to understand the origin of this phenomenon of increasing of mistrust in science. And that I think that there are many types of problems. Sometimes it's the way that scientists speak with the general public. I mean, science are not good to explain science in televisions, and they never learn how to do in most of the case. And sometimes people that hear them may feel they are arrogant. And this they have too confident in their belief. And that may be, you see that if sometimes a bad popularizer present a scientific result as a witchcraft, understandable only by a few selected people, and now people that are non-scientists may take a irrational viewpoint on science that is perceived as magic. And they may think that if science is becoming something like pseudo-magic, why don't choose the real magic? However, also the other problem that we have a general pessimism on our future, and we have all this type of problem. And while in the past we believe that the future will be better than the present, that we have faith in the program, this faith in the progress has been raided, and many fear that the future generation will be worse off than the present. Maybe it's not, I don't think that is true, but just because many people, especially in Europe and the United States, have this feeling, and now science receives the blame for the decline. And the science sometimes is considered as a bad teacher, which leads us in the wrong direction. And in some sense, science general problems that people we have seen also in the last 15 years of elections in the United States, that there's a strong anti-elitism movement in the United States, but in many parts of the world, and anything that presents as new is strongly approved. And the science is starting to, people think that it's starting to be part of the elite, and the anti-elite movement are also automatic along science. Now, what we can do? Now, what we can do is something that we have really to improve the way that science is taught in the school. Now, because education is a crucial point, and it's quite important that young people must be able to understand the general situation of the humanity, the general problem of climate changing, of pollution, of extraction of raw materials, and we have to start to give a more critical way to approach the problem outside, and science is something that is very important. And I'm fully convinced that we have to give children a science education starting the most earlier possible, maybe starting the kindergarten. But there was the famous educator, Italian educator, Maria Montessori, that pointed out a long time ago that scientific education in natural process carried out spontaneously by human individual and is acquired not by listening to words, but through experience on the environment. So and now we need to taught science in this way. We have to do science from children in such a way that they have time to do some kind of experiment by themselves. Of course, it's very difficult to have people interested, but if you just touch the correct things, people will start children will start to do this kind of experiment. And this is very important because the primary function of school is to prepare citizens that may inform a decision. And therefore, I think that the physicists should be more involved than in the past to discuss physics, to discuss science, to speak about science, to communicate science with people, to be involved in the science, in the way that science is taught. And this is something that, of course, you don't need to change your professional things, but if everybody, every scientist, every physicist will spend 5% of his time to try to communicate to people what science is, I think that will be extremely important. Of course, in order to communicate science, you don't need to write books, only to write books or to write papers and so on, but you have to try, for example, to speak with people, to organize in your community discussion around science, because it's clear that you may convince much better people. Also, if you speak to a small community, to an audience of 100, 200 people, and this type of event of science communication becomes frequent, this is going to change attitude towards science. Of course, this is time-consuming. But what is in the stake is our ability to do in science in the future. And if we will not be able to do science in the future in the appropriate way, if science will be not trusted in the future, I think that humanity is going in the wrong direction, and we cannot try to reach something like a sustainable world. And now this is extremely important, and also it's extremely important, I would say, that there's something that people nearly never speak too much about, and there is the way that science really works. Because one thing that is very important is the scientific consensus. I mean, I think that we must communicate the way that science goes on. We understand the method to which a scientific consensus arrived at. And now we have to explain that the scientific consensus is something that is extremely more solid of the result of a single experiment. Because the scientific consensus means that an incredible number of people have written the paper, other people have reproduced the experiment, and so on and so on. So, as you see, we have a lot of communication on scientists that are making mistakes in the experiment. Some scientists that they do some mistakes on the experiment of purpose. They publish things they know that is not true, but this is something that goes on. So also these things is going to undermine the trust that we have in science. And it is quite important that we counterbalance this information with the information how the consensus is reached. And how this consensus, for example, on the on the efficacy of vaccine and so on is something that cannot be bought by multinational and so on. I mean, we have to prove in a concrete way that science is independent from the interest of, let's say, multinationals, of the evil, if you want, in order to show that people can really trust science. Of course, there's many problems, and one of the problems that we clearly have to understand that we cannot really fight the climate change without equity, because it's clearly that we must have some way to in which we must have some kind of transfer of resource for the country which have a higher level of life and countries that have a lower national product for gross national product. This kind of transfer of resources is fundamental if we want to go in the right direction, and also it's fundamental that every country in the world agrees in order to fight global warming. But just because we need some kind of solidarity from different countries, it's difficult to have solidarities in a world where we have the possibility of war, and we have war. I mean, we have actual war. We have a very strong war. We have about 100 million refugees due to various war and disaster. And also we hear from time to time that a threat from use nuclear weapons. And that is something that we have to take out, because if also there are people that speak on a commercial war, it's clear that in a world where you may have a war with real fights and war which is done with commercial war, it's difficult to arrive to some solidarity. And the things that science, we needed to build ties. We needed to build bridges among people of different countries and stress what to unify all human beings beyond nationalism. Science is a worldwide enterprise and well suited. Of course, it takes time, but this is a long-time process, and we have to think on a long-time perspective to which the situation about in this direction will be in 10, 20 years in the past. Now, this has been important, but let me just speak of some successful achievement that the science has done, particularly physics. For example, the foundation of CERN was founded by 12 European countries in 1954. And 3 years before the treaty, where the European Economic Community was founded. And the European Community at the beginning was 6 countries instead of the 12 of CERN. So what we say that science in this type of collaboration was far advanced than politics. In recent time, for example, an incredible achievement of physicists was the creation of the synchrotron light experimental science application in Middle East, SESAM. This is a remarkable laboratory that is located in Jordan, that was founded by a few Middle East countries, Bahrain, Cyprus, Egypt, Iran, Israel, Pakistan, and the Palestinian Authority and Turkey. And now it's incredible that these different countries collaborate with science. Another extremely important result was the whole activity that was done by the Pugwash Conference. This is something like a second-track diplomacy, and the Pugwash Conference of Science and World Affairs which was founded by Nordblatt after just after the Einstein-Russell Manifesto, Pugos played a useful role in opening communication channel during a time of strain of official and unofficial relations, and he produced background work to the Partial Test Ban Treaty, to the Non-Proliferation Treaty, to the Anti-Ballistic Missile Treaty, to the Biological Convention, and so on. So this was something that is very important. The science has done emphasizing physicists was crucial in the past, and the importance of what Pugos had done was recognized by the Nobel Prize, I think, in 1995, Nobel Prize for Peace. Therefore, the actions that physicists can be done is quite large. It goes from technical points in understanding material, weather, and energy conservation, to the problem of increasing the trust in science, to teaching a better science in the school, and also to collaborate in some way that is not so easy these days with scientific exchange between countries, and try to construct organizations that can deal with different strains that we have in order to arrive to a peaceful, sustained web. Thank you so much.
Thank you so much, Giorgio Parisi, for sharing your wisdom, your knowledge, and your ideas. Thank you very much. I am sure that there should be some reactions, some questions in the room. So who would like to challenge Giorgio about his ideas? So Silvina, can you give her the microphone?
Is it working? Okay. Thank you for the very inspiring talk. Lots of ideas. Since you mentioned the Nobel Prize to John Hopfield, and also you mentioned that we shouldn't be talking about whether that's physics or not, but rather what physicists can do, I wanted to ask you how you think that artificial intelligence can be applied for some of the problems that you talked about, the things that we cannot predict, the different aspects of the physics of the relationship between the water and the ice sheet, and also how the CO2 enters the ocean or things like that, and also how artificial intelligence affects this trust in science through social networks.
Well, this is difficult. This is a difficult question. The point is that I mean, in some sense, if we think of model with AlphaFold or other models of this type, it's clear that they may be considered some very complex fitting model in which we fit in a very smart way with a very smart algorithm millions of data, and we have some type of predictions. Now, many people are starting, for example, to do things on of the type that you're saying, on a very, very smaller scale. For example, they look to something that people have very well under control. For example, hydrodynamic simulations on with computer-based hydrodynamic simulations, and they try to see if they can construct numerical models that are going to predict the evolution of the fluid with the same accuracy of the evolutions of the done by solving directly the equation and the microscopic scale. So this is something that is something that is very interesting. However, it's not clear to me how much these things will be feasible in the future. And however, also the other things that I think that maybe is more important is some kind of the reliability. Because when we have a physical microscopic model that's going on, is something that is fundamental. I mean, we know what it is, we understand why it fails, why it maybe fails, and that would be more difficult to do with neural network-based things. That is something we have to, and also we do not have a very long statistic on climate to have any sensible things on based on neural network. The other problem that you ask, well, it's not clear how artificial intelligence is going to the vision of science by the most general public and by the social. This goes beyond my competence. I frequent from some time Facebook and so on, but you know, one lives in his own bubble, so it's difficult to me to say something more in general. But let me add one point. One thing that is quite important for artificial intelligence is that we have to regulate. And we have to regulate because as all type of inventions that are going to modify the way that we live, we need to have some kind of regulations. Let's think of a very simple stuff. The invention of car, automobile. If you don't have any law that is going to prescribe that the way the cars circulate, it's clear that will be a disaster. Now, what to believe that we need a strong effort that we have to do to regulate artificial intelligence, and that should be done by the public power, by the government. But what is also crucial point that the government have to understand artificial intelligence. And it's difficult for the government to understand artificial intelligence as it works. Is most of the research on advanced artificial intelligence is doing in private lab. I think that we need the construction of huge experimental theoretical center on artificial intelligence that are controlled by the public research. For example, one proposal that I'm putting forward, many people are putting forward in Europe, and we are in the process of writing a letter to nations on this point, that one should construct in Europe in a big laboratory on artificial intelligence like CERN. And that will be very important, because otherwise this thing, if we don't understand, if we scientists, which have physicists, we have to contribute so much to the earlier development of artificial intelligence, we do not control anymore what happens in the lab, what happens in the models that have billions and billions of parameters. It's clear that it's very difficult for us to suggest what people should do.
Thank you.
Other questions? Monica?
Yes, ciao Giorgio. Monica Pepaltrelli speaking.
Monica, nice to see you.
Ciao. So just two small comments. I cannot agree with you more on the fact that we should build bridges, and I think that the fact that we all came here to this island in China is the proof of the fact that we really believe that bridges should be built and links should be maintained. Then the other thing that you said is that there is a strong anti-scientific tendency in society, and the trust in science is decreasing. My impression is not for you, maybe it's for our Chinese host, is that here this is not true. My impression is that in China there is a strong belief in science, and this tendency is not as developed as in the West. But maybe our Chinese colleagues can comment.
You heard that Giorgio mentioned this happening in Europe and in the US. Giorgio Parisi mentions that explicitly.
Okay. I think this is not a world phenomenon.
No, it's not a world statement.
That's right.
It is happening in Europe and in the US. I don't think this is the case in Africa or in Asia.
Okay, thank you, Monica, for raising an important question. Maybe I wasn't. That in some sense confirm my diagnosis. The point is the following. If you look to the countries that you have mentioned, China, India, Africa, and so on, it's a country in which the level of life is increasing. And people know that the level of life has been increasing the last 20, 30 years, and this is due to science. So we have a trust in science. Now, if you look to Europe, to the United States, in which the situation is stagnant, and also the middle class is somewhat, we have seen that the inequality index, like the Gini index of economic inequality, be increased inside the Western countries, inside people in the same country. We have seen that the difference between the rich people in the country, the difference of middle class have been increasing. It's clear that the perception of future in these countries is completely different. I fully agree that given the extraordinary success that we've seen in countries like China, but also in the Middle East, in all the East countries, South Korea, Japan, and so on, it's clear that people have no reason to be pessimistic on the future because they've seen that their level of life is increasing. The problem, as your people correctly said, is a problem that is in countries that were rich 20 years ago and 30 years ago, and the situation is stagnant. So it's clearly that that is something that has to do with the general socioeconomic problem, and the fact that is very good that is not that only a local problem, but it's clearly that if the problem is in the country like the United States, which consumes that has the most higher per capita index of energy consumption, it's clearly if people are not convinced of that and do not trust science, that may lead to some disaster because it would be much more difficult to go in the right direction.
Thank you so much, Giorgio, for this inspiring discussion. We have to stop the discussion. We are now out of time. Thank you very much, Giorgio.
Welcome.
So this session is closed, and we move to another part.
I am sorry, I saw the hands go up. This is the first time I've had to give the signal to the audience of 0 minutes left. Now, one of the things that we do as humans is to get together to consider concerns. The Intergovernmental Panel on Climate Change is one of the ways we get together. Working Group 1 is one of the panels that certainly pulls together the most amazing reports. And Vice Chair of Working Group 1 is Professor Inez Canaloni, who has got up this morning to be with us. But I need to check whether she is in fact in the Zoom room. There. Yes. Okay, Inez, hello. That's Helena, right? Oh, yes, great. Inez, welcome. And we have your biography. Everybody will be able to consult it. So a very warm welcome. Please go ahead. You have 20 minutes.
Okay, thank you very much. Thank you for the organizers to inviting me to share this presentation with you, and I'm really sorry for not being in person. I will share a presentation. I think I can, yes. Okay. I hope you can see my presentation, and I will talk about some issues related to climate change. And the first thing is related to the current state of the climate. As you can see in this figure, this is the global mean temperature difference in connection or in relation to the pre-industrial period. This means the period between 1850 to 1900. And there is, this information is coming from different international data sets, and they all agree to show this rise in global temperature, but in particular the acceleration of the warming since 1960. And in particular, 2023 was the warmest year in the record, and temperature was around 1.45 degrees Celsius above this reference period, the pre-industrial period, and it was really the warmest year on record. And when we try to identify the contributions to the observed warming, we can separate, or we can attribute this increase in temperature to two groups of factors. One group is related to the natural factors, and this means variations in solar energy, in the solar irradiance, and also the consequences of volcanic eruptions, and also the natural variability we have in climate. And as you can see in this figure, we have the observed increase in temperature for the decade 2010 to 2019. And the contribution from these natural factors are really, really very small. But when we consider human factors, and this means the increase in greenhouse gases emissions, and as a consequence, the increase in the greenhouse gases concentrations into the atmosphere, and also the introduction of small particles into the atmosphere coming from also human activities. And these small aerosols are mostly related to a cooling effect. So human activities are producing, on one side, an increase in temperature because of the enhancement of the greenhouse effect, and also a cooling effect associated to the aerosols into the atmosphere. But when we compare these two effects, what we found is that the human influence can really explain the observed increase in temperature, and that this increase in temperature also is unprecedented, at least in the 2000 years. So this attribution between increase in temperature and human activities is really demonstrated by science. And talking about the increase in greenhouse gases into the atmosphere, what you can see in this figure is the increase in the CO2 concentrations, the global CO2 concentrations since 1980 to present. And there's really a sustained increase that when we compare with information coming from proxy data from the last 800,000 years, what we see is that this the values of greenhouse of CO2 we have now into the atmosphere are really record values from many thousands of years. And the same can be found when we consider the atmospheric concentrations of methane, and there's also a sustained increase in concentration of these greenhouse gases that is really relevant because it has the potential of warming of these gases is really very important, and the same the values of the concentration we have now into the atmosphere are really very high in comparison with at least the last 1,000 years. And this is also, this concentration is also showing an acceleration during the last years. But when we compare this information coming from concentrations associated to emissions of, for example, carbon dioxide, what we see is that there is also an increase. And in particular, we look at the last years, there's only a small decrease in 2020 because of the pandemic, but the reduction was around 5%. But after the pandemic, the year following, there was again an increase into the emissions. And when we explored where these emissions are coming from, they are mostly related to the burning of fossil fuels, in particular coal, and the second most important is related to oil, and gas is in the natural gas is in the third position. But also we have important CO2 emissions coming from changes in land use, mainly associated to deforestation processes. But it's important not only to have the picture of the global emissions of CO2, but also to have an idea of the regional distribution of the regional distribution of these emissions. And this is what you can see in this figure for the top emitters of CO2 and the evolution during the last 23, 24 years. And there's a sustained increase in the emissions coming from the global south, from developing countries as China or India, but there's a small reduction in emissions coming from the global north, in particular from the US, but also from Japan and Europe. But the full picture we can compare when we explore not only the emissions, the regional emissions, but also, for example, the per capita emissions from these top emitters. And we can see also that even when US is showing a reduction in the emissions, when we consider the per capita emissions, these countries are at the top of all the CO2 emitters. And the slight reduction in the per capita emissions are also seen for Japan and for the European Union. And the per capita emissions are increasing in developing countries as China and India. And now for years, for example, the emissions of China, the per capita emissions of CO2 for China are comparable with the emissions coming from Japan. And which is the situation, the current situation of climate, if we explore the last 2 years, 2023 and 2024, for example, what we can see in these two figures are changes in sea surface temperature for the world oceans, but also for the North Atlantic Ocean. In gray are the last years from 1990 to 2020, and in blue is 2023, in red 2024, and what we can see in the case of sea surface temperature is that they are outside what we have in the previous years. They are in a range of much warmer temperatures than we have in the previous years. And when we also explore what has happened to the ice extent, also at the global scale, and for the Antarctica, what we can see is that the values of this ice extent are really below of what we have also in previous years. And finally, the comparison with global temperature also shows that the temperature was at record levels for these last 2 years, in particular for half of the second half of 2023 and almost the first half of 2024. So the current state of climate is really unusual when we compare different indicators from the last 2 years in comparison with previous years. And which is the future of climate? This is what has been happening and what has been happening during the last years. But what can we say about the future? And to explore the potential future, we prepare climate scenarios. And to do this, we consider different emissions scenarios. In particular, we are working in the IPCC with 5 different scenarios of CO2 emissions. The lowest one, the more optimistic ones, are the ones in blue, that shows a steady reduction in these emissions. And we also have more pessimistic scenarios, those in red, that shows an increase in CO2 emissions for the rest of the century, or a slight reduction more close to the end of this century. And in yellow, we have an intermediate scenario with stabilization in the emissions until mid-century, and a reduction from then until the end of this century. So using these scenarios and global climate models, we can produce this kind of projections of what we can expect under these different scenarios to what could happen with global temperature. And what we can expect is, in all of these scenarios, from the more optimistic to the more pessimistic, an increase in temperature for the rest of this century. But the amount of this warming obviously depends on the scenario we consider. For the more optimistic scenario, we can expect an increase of temperature of about 1.5 degrees in comparison to the pre-industrial level. And for the more pessimistic scenario, the scenario that we call the 8.5 scenario, we can expect an increase of temperature that is above 4 degrees temperature. But we can also produce scenarios of what we can expect in relation to the sea ice extent in the Arctic, or for the global mean sea level. And in the case of the sea ice in the Arctic, there's, for all scenarios, a reduction of the extent of the area of sea ice. And for the intermediate and for the more pessimistic scenarios, from mid-century, we can expect to have periods of area of the Arctic being ice-free. And in the case of the global mean sea level, also there's an indication of an increase, and the amount of this increase depends on the scenario we consider. But these are two cases, two indicators that what we expect is that changes are irreversible for the next centuries and even the next millennia, because of the forcings that are producing these changes and the time it takes this system to respond to this increase in CO2 concentrations into the atmosphere and in consequences in the global temperature and also in the sea surface temperature. So which are the current climate policy responses to what has been happening to the climate and the projections we have for the next decades? And in this context, we have the Paris Agreement, that is a climate treaty that was signed in 2015, that all countries that signed this agreement committed to keep the rise in global temperature well below 2 degrees in comparison to the pre-industrial levels, but also invites countries to make effort to limit this global temperature target to a more ambitious target, and this means to limit the global warming to 1.5 degrees. And the current situation, according to the observed trends, we have in CO2 concentrations, in CO2 emissions, and what has been happening to global temperature is that we would exceed this most ambitious target, the 1.5 target, during the next decade or so. We are really very close to this Paris Agreement target on temperature. And this is the way the world will look like when we reach the 1.5 global warming target in comparison to the 2 degrees target, and also how the world would look like if the global temperature increases 4 degrees in comparison to the pre-industrial levels. And what we see in first place is this half a degree that we have when we compare the two targets of the Paris agreements are really relevant, because consequences are different in different regions of the world. The temperature will increase more in continents in comparison with the oceans. In continents is where we live, where we produce our food, where we depend on water. So this half a degree will produce in some regions increases much more than 2 degrees, for example, in the Arctic. And a world with 4 degrees global warming with produce in the Arctic an increase of over 7 degrees. But these changes in temperature will also impact other variables of the climate system. For example, this is what we can expect that could happen in precipitation for these 3 different scenarios according to different warming levels. And in green, you can see regions where temperature will increase, and in yellow or brown, regions where temperature will decrease. And under these scenarios, those regions that are usually the regions that are more rainy will continue receiving more precipitation, but the dry regions of the world will become drier and drier. And this is what in the jargon of climate change, we usually say that rich will continue becoming richer in terms of water availability, and the poor will becoming more and more poor in terms of less water availability. So climate policies to fight against climate change are basically 3. Adaptation is one of the most important, because we have we are already seeing the impacts of climate change and how climate change is affecting the most vulnerable regions or the most vulnerable populations, even in rich countries, but also indicates an increasing risk for the near future. And the other strategies are related to the reduction of emissions, and this is what we call mitigation. And the other strategies related to how we can reduce the concentrations of CO2 we already have into the atmosphere, and this is what we call the carbon dioxide removal.
Ines, we have 1 minute to go.
Oh, sorry. Okay.
1 minute to go.
So when we consider these different policies, this is the actual situation. We have very ambitious policies to reduce emissions, to limit warming to 1.5 or to 2 degrees. And there's a large gap between what the commitments we have under the Paris Agreement on what is really happening. And this indicates that temperature will increase to above 3 degrees. So in this context is that where the removal of carbon dioxide is really relevant. And this is the way what we call to reach negative emissions, and the technology we can use to produce these negative emissions to remove carbon dioxide from the atmosphere are different. For example, afforestation, and also to produce bioenergy, capturing the carbon dioxide from the atmosphere. So there are new technologies to complement these current policy responses. I don't have enough time to explain them, but I will finish with this. The idea is that this is the way climate impacts are continue increasing in terms of the emissions, the trajectory, the pathways we are having on CO2 emissions. If we cut emissions aggressively, we can reduce the climate impacts, but this will take time. And the progress we're doing is really small and slow, and we can remove carbon dioxide from the atmosphere, but this also takes time, and is the technology in a scale that we don't have now. So there's really a gap, and this is when new technologies are coming to produce this reduction in the near term of the temperature, what we call the solar geoengineering. These technologies implies introducing aerosols into the atmosphere, or other technologies like doing marine cloud brightening, clouds more to allow clouds to reflect more solar radiation back to the atmosphere. So I will go straight to my conclusions or takeaways on this. So the current policies we have are leading us to a warming of about 3 degrees, but with uncertainties. 1.5 degrees, this ambitious target of the Paris Agreements, we will cross this target around 2030s if we continue this pathway of the current emissions. So to reach the targets of the Paris Agreement requires strong reductions in greenhouse gases emissions in this decade. This decade is really critical. And there are new technologies that are controversial, that aims to reflect more solar energy back to space, that are being proposed to complement these emissions reductions and also the adaptation strategies. But it's important to keep in mind that these technologies do not address the root cause of climate change, and could also be used in some way to buy time until we do really need to do, that is to reduce the greenhouse gases emissions in as soon as possible and in a significant magnitude. So this is it, and thank you. Thank you.
Great thanks to you. You have taken us through absolutely magnificently. So I'm afraid that we must move on, and we're moving from the air to the surface of the Earth. And on the line, I hope we have, we are going to be looking at someone who is at present in Cairo, who's sitting very close to the African Rift Valley. Now, we're now going to consider the issue of geophysics, earth science, earthquakes, volcanoes, and tsunamis. Hello, Gad, are you there?
Yes, I'm.
Brilliant.
Good
Very
afternoon
well,
to all of
thanks.
you, and good morning for those who are online somewhere out of China.
Professor Gad El-Kadi is the director of the African Disaster Mitigation Research Center. Who better to consider this? Gad, could you put on full screen for your slides? That's perfect, thank you. You have 20 minutes.
Okay. Do you see my screen now?
Yes,
Did
and
you
we
see my
wish
screen?
yes, we do, and we wish we were there.
Okay, I will be on time. Anyway, thank you very much for the introduction, and thanks for inviting me to give presentation here today with this very important intercommission meeting. I will talk briefly about our effort of monitoring geohazard in Africa, not only in East African Rift, starting from Egypt, of course. The content of my presentation will talk about our history and facilities that we have enabled us to work with our African brothers and sisters, then capacity building programs and ongoing projects. We at NARIAGE is the Egyptian National Research Institute of Astronomy and Geophysics, who started 1839. We have more than 120 years of experience dealing with natural hazard, not only earth science, but also astronomy and space science together. We have a lot of experience with our colleagues and brothers from Africa, from Middle East, from Arab countries. Our institute was moved from place to place according to light pollution, which was one of the main obstacles for astronomical observation. But it is now in Helwan since 1903, and it was named Helwan Observatory. For those who follow earthquake data from Middle East, they can find Helwan Station, one of the long-term available station for monitoring seismicity in the Middle East and Africa. Our facilities, we have what's called National Observation System, composed of astronomical observatories, space science observatories, the National Seismological Network, the National Geodetical Network, geomagnetic magnetic observatories. We have many other facilities around the country, more than 150 locations of live observation for all Earth system observation. On regional space and through bilateral collaboration with our partners, we have also our regional observation system of seismic station and GPS for crustal deformation and geodynamics, monitoring natural hazards like earthquake, tsunami, volcanoes around the continent and nearby in the Middle East is very crucial for us. So we should know what's going on this varying Earth systems. Through both the regional and national system, we work together with African colleagues since we're African, so Africa in our heart. We work together with the African Union, with some other foreign funding agencies like JICA in Japan, African Bank. For last 4 decades, we have trained more than 250 African young researchers on astronomical observation, seismological observation, volcanic observation, and many others. Through this training and capacity building program, we start to have our network with African institutions, building their own capacity, and due to some financial issues that was stopped for some time. So recently, since 2 years ago, we start to activate it with African Union as well. But through the available data and observation system, either both local and regional one, with our partner, we keep monitoring seismic hazard for North Africa, and we publish a good paper that include the map for natural hazard of North Africa, which is very important for many strategic projects working in these countries. But for the whole continent, we also work and produce seismic tectonic map, and this already on sale through UNESCO is for like 10 euros, but it is some of the available information. And also we tracked and monitored tsunami hazard through Indian Ocean, the eastern part of Africa, which is very fragile. Many earthquakes happen in Pacific and Indian Ocean. We still remember Sumatra earthquake, which caused a very huge tsunami. It marks the International Day of Tsunami, which is November. Together with UNESCO on Arab scale, we are also working and producing natural hazard for Arab region, and this is again very important atlas, including a lot of vital information about socio-ecosystem and resilience and adaptation for development, sustainable development of this region. And since we are looking for sustainable development, sustainable long-term programs of capacity building, so we should look for energy resources. Especially Africa has a very high potential for geothermal resources. We publish a work-related geothermal map for Africa, which marked many high potential location could be used for energy production as a kind of renewable energy could help reducing carbon emission as in this symposium, some presentation will talk about it. We hosted many bilateral and multilateral meeting and seminar to disseminate information. This was the Joint General African Seismological Commission, where we exchange ideas, new research with all African and Asian researchers in the domain of seismology, natural disaster, volcanology, and many other related fields. And back to back with such kind of workshops and conferences, we host short training course for young researchers from Africa. But you know why Africa has the most world top fragile states? We have here South Sudan, Somalia, Democratic Republic of Congo, and many others. And here you can see life expectancy for African continent on different scales. But fortunately, we can say Africa is the most young continent. Almost 70% of population are young people. That's why we have to invest in such capacity building program to engage those young researchers to protect the continent from natural hazard. On the other hand, Africa was, most of the African city was only small 1 or 2 stories building, and even this kind of natural building, but now they're shifting to sky towers and skyscraper towers, which is very crucial to have seismic hazard map and seismic loads and many other natural hazards. Otherwise, this kind of investment will be interrupted and lose a lot of money. Together with the African Union, we have established what we called African Disaster Mitigation Research Center, ADMIRE. And ADMIRE is considered as a center of excellence for the African Union since March 2023, where we work with all partners under the umbrella of African Union to monitor and mitigate the natural disasters in Africa through this current activity. But you know, Africa has different culture, different society, different environment, and different economic as well. And the technological availability at these countries is not equally. So we have to consider this in our approach. We consider as holistic approach to tackle such kind of obstacles all over the continent and works mostly with those colleagues. We had both some major objectives to admire. One of them is to operate online because, you know, traveling across Africa all the time could be not easy and not cheap and not safe at some times. Some places where there is a natural risk, it can be difficult to send our crew to work there. So, and of course, after the pandemic, we had learned to work and go online all the time, so that now I'm online with you from Cairo. Availability of geophysical data for geophysical and climatic model, assess the current natural resources available at this location, so we can build on their sustainable development goals of United Nations. Building a scientific network of experts to foster collaboration and promote knowledge transfer among African. Disseminate results by encouraging their inter-availability of data. Last year, we had some building capacity program. One of them was Democratic Republic of Congo and Sudan, Equatorial Guinea for seismic network. And of course, we also built on our long-term strategic relation with international partnership through UNESCO. We had a good agreement with China Earthquake Administration, who visit us and some other location in Morocco. We are going on to have some facilities and joint activities with them in African. Through research, now we have 2 working projects for North African, protecting cultural heritage from natural and human-induced risk, and with Nigerian colleague to build their seismic code, which is very important for different strategic project in Nigeria. You remember last year we had 2 mega crises in Africa. One was the Marrakesh earthquake. It was in September 2023 with a magnitude 6.8. A lot of damage, many casualties, you know. And there was, due to climatic change, the flood at Libya. Also, it was in the same month in September. So we work with all colleagues at both countries to learn lessons from these crises and build their own capacity. Funding from Egyptian government, we had organized a capacity building program for natural disaster monitoring and risk reduction in Africa. That was last year. We had some master and PhD participants from 28 countries through 3 weeks, hands-on data, how to learn from lessons, how to disseminate some knowledge among them, and have some thoughts about reducing risk and mitigation risk in these areas. But only not capacity building, but we focus on capability building, because we may train some colleagues, but they don't have equipment, they don't have facilities. So we need, or we are looking for capability of those colleagues to work. A few years ago, exactly 2021, there was 2 consecutive volcanic eruptions at Goma, Democratic Republic of Congo. We have been there together with all colleagues interested in volcanic activities in East Africa. We met the Minister of Scientific Research. We support them with sub-equipment for continuous monitoring of volcanic activities and seismic activities there, and working together 24 hours for live monitoring of volcanic eruption. With Sudanese colleagues before the conflict, we helped them to build their own seismic network, monitoring seismicity and risk for hydro power dams is very crucial, not only to Sudan, to many other countries in East Africa, which is famous with seismic activities. We built and hosted African Seismological Center. This together with African Seismological Commission, which was one of the founders, and the second and the first vice president of the African Seismological Commission from Admire, Nariaj. Hosting this data center, computational power will enable our African colleague to have accessibility on the data. This is just example of some current project for protecting culture heritage from natural hazard. One of the main obstacles among our African colleagues is to provide sensors. So we work together with our partner to have low-cost sensor for seismic monitoring, for tide gauge monitoring. I will go quickly on this screen because it's technical data, which has real-time plotting of the measured data, and have early warning about if there is an accident or earthquake, or there is no prediction, but early warning, which is very important for such to keep the life of the people around the center. Air quality sensor, weather station, and this is just an example of Muhammad First University in Morocco, where we work also for protecting culture heritage sites. Here the facilities of Admire within Riyadh facilities in Cairo. The building is one complete floor in 3 stories building, equipped with meeting rooms, facilities room. We hosted one of international training program with CTBT, Comprehensive Treaty for Banning Nuclear Tests.
5 minutes.
Yes, I'm going to finish soon. Thank you. And here you can see on the screen live monitoring of many earthquake and volcanic eruption and weather station worldwide, and we have some section for Africa and of course to Egypt through our regional and national observing system. Here is one of the training program, and this gentleman is General Secretary of CTBT. Many training session working on with African brothers and sisters. The center or the meeting room equipment with a screen, so people can work simultaneously with the teacher on the data. Site testing for equipment, for checking any technical error in this one, and of course catering and very delicious food of the Middle East. During this year we have many program for capacity building, content with the Sudanese seismic network, Equatorial Baba Guinea, volcanic eruption monitoring at Goma. We are working together with all colleagues at this different 8 joint project. That was an example of our program for capacity building of last year, and we're going to host this again this in December, and communication being sent to relevant representative of African countries. And during this next month, November, we are going to host a workshop for bridging innovation in disaster mitigation for a resilience future of African. That should be from November 19 to 20 in Cairo, headquarters of Admire. Preparation are going on. And of course, we try to disseminate some practice, new manual for seismological observatory that we learn also from our international partners. That was from GFZ in Germany, and we translate partly to Arabic to get some benefit for Arab-speaking country. And those our partners from different countries in Africa. And of course, we acknowledge the financial support from Egyptian government, different funding body. And that's all my presentation. Thank you very much. I'm ready to answer any question or even later on through email or WhatsApp. Thank you very much.
Thank you very much indeed for taking us through and giving us an early warning of what things look like. There is work for physicists here. Can I ask whether Professor Jiangang Li is in this room? We are ready for you. We are ready for you. Professor Li is director of the Energy Research Institute in Hefei and is also Oh, we haven't got time for questions right now, but on the program, if you have it in front of you, you will see that there is a discussion time coming up. Thank you. So, is very much involved as a plasma physicist with the provision of energy through the experimental advanced superconducting tokamak. Over to you. We need the slide here.
First of all, let me thank the organizers who invited me to be here. Thanks for your nice introductions. And you know, the China facing extremely challenging for the CO2 and reductions. And since, as you know, we are the #1 CO2 producers, and which is even more than the top 3 other countries. So for the past 20 years, Chinese government and the people make great efforts and for clean coal technology, renewable, the energy and the nuclear. Last month, then, we are going to build another 11 nuclear fission, which makes the total number of the fission reactor, and in China will be 104. So, which is #1, will be #1 in a few years. And same times, they also Chinese scientists make effort to trying to make these fusion, which is one of the most challenging future energy. As you know, the fusion. And we already spent more than 50 years, and we still not find a solution yet. And in China, we have these 2 approach, and one is by lasers, and the second is my field by using the magnifying confinement, so-called tokamak. And for the tokamak, you need at least 2 tough jobs. First, you have to burn the plasma to the ignition conditions, which are the minimum temperature 100 millions. Second, to sustain this is hot air plasmas continuously and for whatever long you wish. And China, 20 years ago, nearly 20 years ago, we joined the ITERs. You know, the ITER, International Thermonuclear Reactors, which are built in France, is the almost the largest scientific project, and by more than 30 countries. And at the moment, we have a few small tokamaks. By joining the ITERs, and China make a jump and to the large scale of the nuclear fusions, and especially from tokamak approach. And this is 20 years ago, we had these versions, and we think after joining the ITER, and we learn the technology and working with our international cooperators, and we can build Chinese fusion reactors, and which has demonstrated in the fusion reactor levels, 1 gigawatt continuous running. After that, and we can approach the prototype power plant in the 50s. And this is a guideline to, we followed since 2010, and starting from the small tokamak called the superconducting tokamak East. And this is the first superconducting tokamak in the world, which is all the magnet field, and it's produced by superconducting magnet, which is also very difficult. You have to, and fast ramping the current to control the plasma current. And this is a machine actually, and for the 15 years, we achieved the 2 conditions. The first, we successfully to get the plasma up to 100 million degrees. Secondly, we can maintain this plasma to whatever long and we wish. And for example, the ITER are going to be run the plasma at 100 million for 400 seconds, we call the edge mode. And this is one of the charge, and a few years ago, and we get 100 million degree, 400 second edge mode, which is similar to the future ITERs, and also repeatable. So the laser has some kind of problem you cannot repeat. And even you want next time, but you may not get it. So to repeatable plasma is a key to have the future energy. So you see, we can repeat this, even after a few days and a few months, and repeat this discharge easily. And 2 years ago, we even can extend the plasma to 1,000 seconds with a temperature 100 million degrees. So with this, we think we can move to the next step. You know, this is only small tokamak and without using the fuel. So 10 years ago, Chinese government make a plan. So we should start designing our own Chinese fusion engineering testing reactors. And this is size is slightly bigger than ITER's, 30% larger, but the performance will be 3 times higher than ITER's. So this is the machines, and with the duty cycle means half a year this tokamak will be running. So with the energy amplifier for 30, and also with the tritium should be produced in these machines instantly. So we built a team from all countries, and you can see we have these 5 groups for physical designing, safety designing, engineering design, and auxiliary, and the database. This is quite active. You can see every year we have these annual meetings, which are around 1,000 people from the countries, and also with the advisors from international community. Every year they have several review meetings for check our designing. And so the parameter, as I said, about 30% bigger than ITER, but the performance about 3 times higher than ITER's. So this is machines we are going to be built. After finishing the engineering design, and this is the layout for the whole site. The site's also similar with the ITER in Kadrash. After designing, the government said, let's do the R&Ds. So 5 years ago, a facility called the Comprehensive Research Facility for Fusion Technology, not for physics, was started in the Hefei. So the purpose for this R&D is trying to establish the prototype technology for the fusions. You know, the fusion is extremely difficult. It's combination for different science and technology, such as superconducting and material, heating and current drive, remote handling, tritium, and nuclear, everything, safety, everything. So with this facility, we're trying to build each of subsystem for the prototype. So it's started 5 years ago, and it should be finished end of next year. So now it's quite good on the schedule. It's over 80% of the system has been finished. This is a list of all the systems. I don't want to explain because it is so technical details. But the stories, and together with the tritium, you know, the tritium, we need to produce the 153 kilo tritium per year, which is a huge amount for that. And for doing so, we not only designing, but also build a test bench and put the tritium material in the fission reactor to testing the tritium extraction and the tritium production and the performance. And after 3 years of the testing, and we found that 99.9 tritium can be produced if your neutron hit the right material. Not only produced, but also you can extract it by special technology to get it out. So that means if in the future, this technology will be alive to the reactor, so the tritium can be produced real timely on this tokamak. So one of the most challenging things is the material. You know, the all the fission reactor need to replace the fuel almost 1 year to 2 years due to the material. So for the fusion, we wish the material can last at least for 20 years or 30 years, then you replace. This needs the material up to 200 dPAs. So this is huge challenge. We don't have the experience and we don't have the material which can sustain for these conditions. And we had a roadmap from 10 years ago on each of the different materials on each test plant. Not only put on the fission reactor, but also we are going to build a neutron source, which is accelerator-driven neutron source. Get very high fluence. This is about 10 to 16 neutrons per second. per centimeter squares. So it's about a similar value, even higher than the so-called IFMIF, which is a joint effort between Europe and Japan. And with this kind of designing, you can see each test sample can reach 60 dPa per year. So 3 years operation for this, that can be quantified for the 200 dPa material. So this is a high fluence and the facility, but which is not start constructing yet. But we already spent 10 years for R&D. For example, the accelerator, continuous high current accelerator, the target, and also the remote handling material things for that. And so hopefully from the year 2026, this facility can start to be constructed, which will take 80 years to constructions. And as you know, the ITER is delayed about 10 years, unfortunately. And this is due to the COVID, due to other things. And so that means until 2040s, we don't have burning plasmas. So should we wait until that? And until 2050, according to our previous roadmap, until the 2050 should be the time for the tokamak to be, to start commercialized. But if we wait until 2040 and have the burning plasma, this will be impossible. So, recent few years, Chinese government decided let's do speed up, and by building a small tokamak, which is about 10% of the size, but 30% performance of ITERs, and called the burning plasma superconducting tokamak, and to fit here. So together, the performance is smaller, less than ITER, but early you can have the experience, not only scientific for the burning plasma physics, but also you can combination the future demo relevant technology together. So this is what we decided 3 years ago. So the machine for this machine, and we call it BEST, very good name. So that could bring a bridge between present machine to ITERs. So the ITER will be Q equals 10. This one will be Q equal 1 to 5. And another thing, this one will be long time operation. Steady state operation means hours operation or even days operation. This is different with the ITER. ITER only operates 400 seconds without real-timely tritium breeding. So this can be another testing facility for breeding the tritium, which is needed for the future reactors. So the objectives, we have these two steps. First, to quickly get equal, Q over unity, and then Q equal 5, which has the condition for the burning plasma in the future, Q equal 5. Second, to try to quickly to get the long pulse. And long pulse means a few hours at least, and which the tritium can produce and extract, then fill back into the tokamak. So we can finish the full cycle for the tritium. And so this is a size. We quickly designed this machine based on the experience from the previous small tokamak East and also the ITERs. And 2 years and has been used for all the designing. So the beginning of last years, we started construction of these machines, And you can see the building will be like this, So very beautiful buildings. And also we wish this also will be a very beautiful facilities. And I just show some pictures. And most of them has finished. And next year, all the building will be finished. And at the time scale, we wish we can make this happen end of 27. So we had this extremely heavy load on the schedule. And partially, due to the, in the beginning it has the COVID, but anyway, we're trying to catch up the schedules. And after 27, we wish we can spend 3 years, and to get the target Q/1 and Q/5. So this is a relatively challenge for us. So as a summary, China make this significant effort for the past 20 years since we joined the ITERS, and working on it, and together with other future energy, especially renewable fission, and we also make these generation 4 fission reactors, which is the high temperature gas cooler, starting operation 2 months ago. So we wish we can finish the construction of the demo in the year 35, and starting the commercialized in the year 50s. And if this can be happen, and the clean energy and for the CO2 suppression, and will be much better condition than now. Thank you very much.
I'm sorry that we I'm sorry that we can't take questions right now, but we will have a discussion session in a little while. That is a whirlwind of fusion advancement. So we're now going to broaden our view of energy and look at energy in general. And Professor John Samseth is not only a member of Working Group 21, but the chair of the Scientific Committee on Problems of the Environment. So he has an overview of energy. Now, after his talk, we are going to head for coffee in an incredibly well-constructed way, with hopefully a production line, because we'll be back soon after that. Thank you. John, over to you.
So thank you for a nice introduction. I should like to mention that the first people thinking about climate change was really the people in the scientific committee of the problems of the environment scope. And those people later formed the IPCC. But unfortunately, the scope's name is not connected to climate change, although we were the first. Anyway, it's a great honor for me to come here to talk to you. I'd like to thank the organizers. And I'd like to mention that I was also here in June, and then I talked about bioenergy. And I was invited by the Chinese ambassador to Norway to celebrate the 70th anniversary of the relations between Norway and China. So, the fonts are different from what I had. So anyway, this is such a vast topic, so I'm not able to cover anything, so I'm just more or less going to give you some examples. So solar energy, let's start with solar. So the dominant one is photovoltaic, and we have several ways of harvesting it. It's through active solar energy, which you track the sun, or the passive, or the one with solar cells, as you know, or you can integrate into buildings. Concentrated solar power, that is then to get industrial high temperature heat, not high temperature, and also in some cases electricity generation combined with the heat production. Then the domestic use is essentially solar thermal energy for water heating, district heating, and then maybe if you want to have low temperature heat for industry. So the market today is that PVs are rapidly expanding. Solar thermal energy peaked in 2021 and is down 30% by last year. But there's a new market emerging, and that is solar cooling. Also, it's emerging is a combination with energy storage. That can be a battery, but also thermal storage in forms of kind of some liquid salts or something like that. Oops, I think I was making my presentation on a Mac, and this is a PC, so I'm sorry that doesn't come out very well. But anyways, PV technologies comes in different generations. So the first generations we have is the traditional monocrystalline silicon. That is dominating the market, and it has increased so much that is even taken over the second generation market, which is the which is the thin films. So the thin films has not really made it through because the efficiency of the monocrystalline has not reached such a high level that it's hard to compete. So the problem is now is really on the third generation, and they are still, most of them are in the research labs, the dye-sensitive solar cells, organic or polymer-based solar cells, perovskites, nanocrystalline solar cells, and the concentrated cells of these. So, so the silicon base then dominates because of the high efficiency, 25%. In this large solar plant you see, it's essentially silicon and cadmium telluride that are used. The problem is that cadmium is a very poisonous substance, so one tends to not use too much of them. But what I find the most exciting is the new solar cell that will come here very soon. It's the plastic cells or organic solar, but they are not commercialized yet. So they have reached 19% in the lab. Note that 19%. And there's a high chance of them getting much higher even. Oops. So this is one of the most modern solar cell parks we have on the planet. It's in Dubai. It's a mega park, they call. And it's supposed to reach eventually 5 gigawatt. And when you take the capacity factor into account, this corresponds to 1 nuclear power reactor. So it's a combination of the various forms of harvesting both photovoltaic, but also then thermal through solar tower and the parabolic mirrors. It will produce then both heat and hydrogen. And the tower is record tall, 263 meter high, and it has capacity of 100 megawatt. It also connects the liquid or the heated liquid, and is then stored in a energy storage, about 6 gigawatt hours, which is also tremendous. That means that you will have energy available also when the sun is not shining. And this is an example. This is not the same park, but it's a sample of this parabolic trays. Solar PV is also then installed into new buildings. So it's very common now to have in new buildings in probably here as well as in Europe and the US. There's a lot of new large stations located in desert-like areas coming up. And most of these new parks are mainly PVs, because you can usually then integrate this into the grid without storage, because that's the cheapest way to do it. Solar cells are really easily to fit into existing building, but they also can be put into new components like roof tiles and things like that. So this was nice and clear. So this is the way we do it today. Solar panels, silicon solar panels on the rooftop. This is the future, where the tile itself is the solar cell, monocrystalline crystalline in this case. This is an example of the largest solar park in the world. It's a PV solar park in China. It's 15 megawatt electric. and it covers 420 kilometers square. And it's planned to expand until up to 600 kilometers square, which corresponds to the area of Singapore. So this is 15 megawatt electric, which correspond to 4 reactors. So 4 nuclear reactors is equal to the size of this thing, covering 600 square kilometers. Now, as I said, an exciting thing happening now is with the organic photovoltaic cells. And they are organic semiconductor electronics that use small organic molecules or conductive organic polymers to absorb light and generate charge carriers through the photovoltaic effect. So this is kind of the same way as the silicon. And they can be structured in monolayers, bilayers, tandem, heterojunction, etc. Now, the nice thing is that they are very simple to process. So you can process them using low energy processes, such as printing, press casting, spin coating, etc. So you don't need high temperature or a lot of energy to produce them. And they work in the traditional way for solar cell, but you should note from this slide that they use what we call these exotic molecules. These are molecules that were discovered or synthesized for the first time maybe 25 years ago, the buccal fullerenes, and so on. So now we see in one of their important applications of them, discoveries that were made a few decades ago are now coming into a large-scale usage. So they can, since these then are dissolved into liquids, you can print them and you can mix them as much as you like, so you can kind of compose very intricate structures, which helps improve the efficiency. So the simplest one is the one with the active one monolayer. You can double layers and so on, and you can multi-layer and everything. So you can print them as you are printing text on plastic bags. You can be like an artist. You can create artistic solar cells. This is like a leaf. Now, there are some important issues with them, though. Since they are made of plastic, you have to think about, the water or moisture penetration into the cell. They are not very good towards heat. You have to be concerned about solar radiation, concerning UV, and also the mechanical stability. They are not very mechanically strong. So degradation and stability of the absorbed molecule is an issue. Oxidation and water penetration, mechanical degradation of device. Heat tends to also affect the stability and also the stability between interfaces within the cell. Now, this is one of the new applications coming up. You can then integrate them into textile. And this is one example of a Dutch designer, wearable solar dress. And the latest thing out of Germany, organic PV sunglasses. So the research needs, for the young people here, materials, design, integration, and better manufacturing processes, and recycling of solar cells. It's very important. Hydrogen. It's for reducing greenhouse emissions. And it's introduced because they want to decarbonize industry and transport. And I enlightened industry because I think that is where they will be more important than in industry. So there are some issues: low energy density by volume, a tiny molecule that can escape, makes metal brittle, safety, or they must be stored and as liquid as 20 K or as a compressed gas, safety issues, no market exists, difficult to transport, but they are much better than to convert them into other potential fuels, methanol, kerosene, and ammonia. It's better on that screen than on my screen. But anyway, this is, you can combine it and take the lower part there with CO2 or nitrogen to produce these synthetic fuels. So, but the trend is not very promising for hydrogen vehicles. There's a sharp decline in sales in all markets except Korea. So the sales fell then in 2023 by 30% to less than 15,000 vehicles. Filling stations are being closed. However, battery electric vehicles sales were up 30%, up to 10 million cars. So essentially, we can say that hydrogen cars are not the future. And if you look at the US, the sales levels on the first quarter this year was the same as in 2015. So a recent trend, there has been a massive financial incentive to promote hydrogen, but despite all these incentives, high-profile projects are cancelled. So the pipeline that was supposed to go between Norway and Germany to pipeline hydrogen made in Norway has been cancelled. 6 mega projects in China has been cancelled. The Nordic energy companies are just halting all their projects. So the future of hydrogen, that will be as an industrial gas and not as a transportation fuel. And it will be used for feedstock to produce e-methanol, e-ammonia, e-kerosene, and also for the fertilizer industry and for the refining industry. So the research needs with respect to hydrogen is how to use it directly into metallurgical processes and to substitute in cement production. E-fuels. Oops, getting short here. So it will be then used then to, that is fuels, essentially e-methanol, e-butanol to kerosene, that are made from hydrogen. And there are targets, so there will be a big market for these things because you can't have battery ships. So both for aviation and shipping, they will be very important. And e-ammonia is emerging as probably the winner in shipping because there is a market in place and there's a lot of demand for it. However, in all these processes, in making e-fuels, there's a lot of energy losses in form of energy, thermal energy. So, in a way, they are kind of very inefficient. But this one way out is to combine it with the biomass gasification and electrolysis of water. Then you can double the fuel you can get out from the biomass. So, and that is what is going to be called e-biofuel. So there the energy loss is not that much, and we use all the components to get out of the electrolysis, oxygen and the hydrogen, both of them are being used. So due to the low efficiency of both combustion engines and fuel cells compared to electric motors, chemical fuels will only be used when there is no electric alternative. So keep that in mind. The efficiencies of these chemical processes are simply enormous, so they can never beat electric. So land-based transport, the future is fuel-free. Nuclear energy. And the reason why I wanted to add nuclear energy was that right in our neighborhood, something important is happening. So there's a surge in interest for nuclear energy, excitement about small nuclear modular reactors, and commercial light water reactors will be only deployed after 2035. But there are a lot of designs, so 100 designs have been proposed, but only a handful will then never be built. And we will see floating nuclear power plants, maybe even ships running on nuclear power. But there are many new nuclear nations like Egypt, Turkey, Bangladesh, and Ghana. And China has the 2 reactors that are intended then for exporting. So we'll see them all over the world. Now, the non-electric use is emerging, like for desalination of water, which is going to be a very important part of the planet. District heating, and then to produce ammonia and hydrogen out of methane. So this is the future nuclear fuel cycle. We start with the mining, fabrication of fuel into the light water reactor, then reprocessing. Some fuel go into the advanced burner reactors. Some are stored and and some are, yeah. So this is kind of a very complicated mesh, and there's a lot of research needs associated with this entire process. Everything from fuel production to processing, reprocessing. So we need new materials for extreme reactor core conditions, corrosion-resistant material that's so important for the new reactors, molten salt chemistry, heat transfer under abnormal conditions, and improved resistance, radiation resistance in the fuel. Yeah, so this, you probably know everything about how a nuclear reactor is composed. Core is the uranium, which is then into a kettle and the steam generator and generate the steam. Now, one export model is the Hualong 1 reactor. It's developed together with EDF in France, and it's originally based on the French reactor. It has active and passive safety systems. Note that it's active and passive, because only today new reactors have only passive. So this is Hualong 1 helping China meet carbon goals. Linglong 1 SMR. So it's here at Hainan. It's the first commercial SMR. It's the first integrated reactor. It has been approved in Europe and will be connected to the grid in 2 years, 100 megawatt. So integrated reactors means that you take all the major components and put inside one tube. So they are simply produced. You can produce them in a factory. And here is the Linglong 1 reactor. Everything is inside this yellow thing. Here is being lifted into the reactor itself at Shangyang, close to here. And the last one is a Vinci micromodular reactor. It has a new type of fuel, so small 1 millimeter diameter pellets of uranium, and you can produce then blocks or pebbles with them. And this is a 5 megawatt reactor, tiny reactor. Looks like this. No liquids, no fluids, nothing. It's just all solid. And it is put into a container, so we can transport it around. The military will have these things. The Red Cross will have these things. And the future is electric with the help of physics. Thank you.
Thank you so much. It's time for coffee. Let's make an efficient way out to coffee. We need to be back at Cyrus 4:30. And we will be starting then. And there will be a discussion time. The slides will be available on the Indico site. As they become available, yes, I have been begging the presenters for the slides. presentation. And not quite as much as that. Okay. Thanks. Right.
Yes, one of the previous speakers mentioned that the trees help to eliminate greenhouse gases, and I was wondering, to what extent are people worried about the number of trees? Because I see a tremendous acceleration in the destruction of trees. Whether it be wood for construction or other products like containers for shipping. All these companies now, people buy products online, and we're just really abusing trees. So I was wondering, to what extent are the scientists studying that problem?
I'm going to take that one myself, because living in Africa, we are extremely concerned about the destruction of the natural biome and the biosphere, which used to be a sphere and is now a few fragments. For example, the planting of trees for palm oil in order to make a living is under the spotlight. It is also known now that it's not just trees. Planting trees is fine, but what we really need are savannas as well. The soil is now known to have an enormous role in removing carbon, in sequestrating carbon, and especially the mycorrhizome sphere, the fungus that lies underneath the surface. It wasn't realized how big that role was until Biosphere 2 was built by NASA to put 8 people out of communication, except for light and communication, for 2 years. The experiment very nearly failed because the value of soil wasn't understood. This is an enormous problem. Our colleagues know it. Maybe we don't. Over here, the Prajval in the orange.
May I?
You've got, yes.
Yeah, thanks. So I had a question perhaps for Halina. Hi, Halina, this is Prajwal Shastri. I was wondering, the technologies that you presented are amazing and show a lot of promise. And of course, we should be looking at technologies to transition to more, shall we say, favorable to humanity kinds of energy production. But shouldn't we also be juxtaposing that against the elephant in the room, which is the consumption? I'm actually looking at a plot for Australia done by the Donuts Economics Group, which you probably have also seen, which shows a planetary overshoot, which is like factors of several. So if we do not juxtapose the promise of technologies against that, then maybe we would be under the delusion that we can just tech fix our way out of this crisis. Whereas what we really need is lifestyle changes, reduction in consumption, more equitable consumption for the well-being of all across the planet.
It's a million-dollar question, I think. Obviously, the balance in the society of consumption and the usage of energy is very important. And I didn't quite address that part, but what you are suggesting is, of course, the biggest dream of us all, to reach the balance in which we learn to live to our means, that we don't destroy the world. Now, it can also, if I would want to slant it towards what I was talking about, I think that what we are trying to do in the development of those new technologies that I was addressing, trying to talk about, is that we want to also make sure that developing those, we are not consuming enormous amount of energy that in order to develop those methods. So they are supposed to be energy poor, and enable us to do things, for example, not having to do things in low temperatures, in developing new materials or developing new machines. But that doesn't answer your question, because your question is more philosophical, and it is whether we can turn to our society and ask politely, or maybe less politely, to look at the consumption in itself and find out a balance in what makes our lives sustainable and what leads us to unsustainable futures.
Thank you. I think Hans-Peter?
Thank you for a wonderful afternoon and symposium, and hearing and seeing different views in a complex problem. I was missing as we talk about sustainability. Sustainability means we sustain. We have not talked much how much we mine and how well we can recycle. Mining and recycling are both crucial and are both energy intense. When we're talking about a circular economy where we recycle everything, we never think, we never consider how much energy that really means. And to me, in all this discussion, I think we have to look about energy that we have to put in whatever process we do, energy that we get out, or energy that it costs, and see, are we sustainable or not? The Earth, the planet, what we mine out basically is a finite resource. And we should not see Earth as something we can excavate forever, for good. The time is in the past where we thought resources are infinite. I do believe that energy resources are vast, are close to infinite, but material, what we mine, is finite. When we think about new solutions, new materials, new quantum, it often means critical minerals. These sensors are complex in the material composition. We use the whole periodic table. How much can we mine? How much can we recycle? And at what energy costs?
Thank you. This takes the discussion into an extremely practical direction. Definitely concerning mining, the use of energy. I think yesterday we came up with the sustainable use of entropy, or generation of entropy. And I think this discussion is extremely important for physics. Coming from a country on the borderline of developing, jumps up and down, very many people don't have energy to put into technologies like this, and are dealing with an entirely different aspect of sustainable development or regenerative development. Great. Who was next? Petra. Who has the microphone?
I have a more technical question to Ines about the climate change. Ines, you show very interesting data on the temperature increasing and trend and projection for the future. One of the typical time you show is about 50 to 100 years. That is exactly the sun changes, basically. I'm not talking about the irradiation of the light of the infrared, but basically the particles injected in the atmosphere. The question is how much we are sure in that in the last century the sun is not a player of this increasing in temperature, because we know very well that in the past there were period of ice, period of high temperature, and this is clearly connected with the sun. We have the Martian situation that was basically an Earth type planet 3 billion years ago and then evolved. So how much you can exclude the sun is a player in this century or in the past century?
Thank you for your question. I show in one of the figures this attribution study about the contributions from human activities and from natural factors like solar activity and volcanic eruptions, and also the natural variability of climate. The contribution of changes in solar activity during the last decades was quantified, and it's around 0.01 degrees Celsius. Is really very, very small compared to the increase in temperature that we observe, and that we can also attribute to human activities. To do that, we use climate simulations. We force these climate models with these different forcings, and only when we consider the increase in greenhouse gases concentrations in our climate models is that we can really reproduce the observed increase or rise in global temperature. This is why we explain that the natural factors are not the reason for the increase and acceleration in temperature rise during the last decades in particular.
Thank you. I'm not sure where the next hand was. So if you could raise it again. While I'm looking out at the audience, I know of someone who did apply for a research grant in order to correlate the production of excellent wine, particularly French wine, with the sunspot cycle. Perhaps we could think of the production of wine in terms of the changes of the sun. But I do know, Ines, that a lot of natural factors have been excluded, including the nutation of the Earth's axis as the Earth rotates. Nathia Chetty.
Thank you, Igor. So I agree with the comment made a moment ago about the access to new materials for the modern economy. Recycling is important, but hardly ever have we talked about the impact of mining on the environment. We come from Africa, and we know full well that the approach has largely been these large multinationals kind of parachuting in and extracting raw materials and exporting this to far-off places. But hardly ever is the human dimension taken into account, the impact on mining communities and the environment, of course. So all of that needs to now be addressed in a much more harmonious way if we're looking at sustainability. But I have a question to Professor Lee. I really appreciate his comment on the fusion opportunities for the future, and I hope he's here. I couldn't quite see him here, but just kind of circling back to the comment that Parisi made about scientists not being good enough in communicating with society. He said that we tend to be overly confident and too arrogant at times. So in the context of the delay with the ITER fusion reactor, 10-year delay, and without any really simple enough explanation to the public. I mean, scientists might well appreciate what's going on, but have we communicated this well enough? It's a hugely expensive experiment. Do we just simply expect that the taxpayers will continue to pay for this? Or have we communicated this well enough? I'd really appreciate a response to that. Could we be doing better with that?
Professor Lee has had to leave in order to attend a meeting tomorrow morning, which I think is to assist in bringing fusion power to us faster. And he says he is available on email to anyone to talk about these questions. Good. Now, Cyrus, how are we doing for time? Okay. How long? Okay. So we have 13 minutes to go. I don't know if anyone would like to make a closing comment, and we have a hand over there.
Okay, thank you. Perhaps not a closing comment yet. Just a question on the consideration of the workforce that's involved in coal industries, for example. I know it's a very contentious point in South Africa, where the need is very much recognized from transitioning from a carbon-based economy. But because we depend on such a large extent on coal for power generation, there's a very large workforce involved in mining coal and then importing coal, and then in the power stations themselves. And so I think for any transition to be successful, especially in the developing world where perhaps the carbon-based technologies are entrenched, one has to make provision for the workforce in terms of how they will transition. Otherwise, you would end up with local, especially rural populations, being very upset with what we might view as progress, but they view as regression in terms of an income. Thank you.
You have put your finger, Rudolf, on the reason why South Africa is not transitioning at the moment. And I think it's very important for those in high-income countries to realize that the political process can stop a transition. There is talk of a just transition and a just energy transition and a just AI transition, but you cannot expect that everyone in, for example, the agricultural industry will be able to move into an AI-related job, nor that everyone who mines coal or is in the coal industry or coal-fired power stations will be able to move into a high-tech job. It doesn't happen. Australia is one of the places where a great deal of work has been put into this. I don't know, Inez, would you like to comment on this?
Yes, you just mentioned the key words, just transition. There are huge differences between global north and global south. And even when climate change is a global problem and we need to find global solutions, it's not the same for every country and for every region. So we need the global north, who are the primary responsible for climate change and the worst impacts of climate change, to understand the local issues that we have in the global south. And that's why we put this conversation in the context of equity and justice also. So this is why it's so difficult to find solutions on climate change, even when we have these global agreements like the Paris Agreement, for example.
Thank you. I think that touches on the two topics of climate justice and climate finance, which we haven't talked about either yet. Cyrus, how are we doing? Okay. So are there any other questions? No? Then I would like to suggest that we actually, is there one? Right, we have a question.
Something I've been thinking about since Parisi's talk was, you know, what physicists can do, not only in physics, but in society. And so, you know, a little bit of what was just discussed has to do with addressing science communication and a lack of trust when it comes to science. But I was thinking, are there other efforts that physicists should be involved in outside of doing physics to address these issues? And activism is one thing that comes to mind, but I'm wondering if there are other things that people are doing.
Michelle, would you like to think about the issue of initiatives that IUPAP can take where we come together as a global entity to either engage in science diplomacy or to influence governments across the world or to deal with the trust issue in science? So we need a microphone.
Science diplomacy or policy statement, I would tend to be very cautious to make any political statement in the present situation, because this will necessarily hurt some parties, and this will not be beneficial to be really inclusive. So I remain on the line, which was the line of which was defended in the history of IUPAP by many presidents, that what we have to do is to use physics to get a better global understanding. So physics for getting people to understand each other. This is our line, party line. We should not go beyond physics for getting people understanding better each other. This is my statement. Now, it's true that we can contribute to through physics, worldwide conferences that we are organizing, this General Assembly, this contribute to better understand each other, but we can go further. This symposium shows that we can go further. We can show that physics can contribute to sustainable development, and sustainable development is a goal which is shared by everyone. So by trying to push physics for regenerative development, we will pursue this goal in a more concrete way of getting better understanding with each other. Thank you.
Something I think that IUPAP can, is this working? Yep.
Yes.
That IUPAP can eventually do is bring together some experts that could produce a report. It would be something like one by one, but like, for example, collecting the types of urgent questions that need to be answered, where physics could contribute to respond to them. And the other thing would be like doing a informed report on the most recent developments in different areas. So it wouldn't cover all the areas that were addressed here because it's too, it's too broad, but maybe we could start to produce some of those reports. And the external evaluation, I'm sorry, I keep on calling it that way, I don't know, advisory report. They told that one way in which IUPAP could gain more visibility would be by issuing reports that could be useful for different communities.
I take that point very well. We're coming to Pietro.
Just a comment, Silvina. I think, your idea is great. I think what we could do is a step further to make a sort of roadmap for this theme, for the sustainability of the planet. We did similar activity in COSPA 15 years ago. Roger Bonnet launched the idea to produce a roadmap for space science. It was 90% of what the team wrote in the roadmap was actually happening. So it worked very well. I don't know, it's just a bit more difficult, but maybe something more to be published and to be advertised.
I don't know. The thing is, this is very diverse and complex. I think that we should focus on something in particular. And let me tell you that IUPAP had for many years a working group on energy that was completely inactive. And so that's why eventually we dissolved it. And then we thought of other avenues like this new working group. But so, because there are also economic issues and political issues, and sometimes it's not so easy to discuss. So I would try to focus on a subset of questions or something like that, and engage our commissions to bring in experts and of course our working groups, and maybe produce one report. And then from there, we could think of others for the future.
We are in fact on the road in the working group. Our members have been essentially listing the opportunities for physics. We have a beautiful list in terms of climate science, where we can make contributions that become transdisciplinary, where physicists join the team and use their expertise to connect with other scientists. So we have some of that material coming up. With the restructuring, maybe we can talk about how to do this. I know that the previous working groups had the difficulty that volunteers for example, need to be encouraged very considerably in order to deliver on something like this.
Yeah, that's the problem. This is a huge problem.
But we can talk it through, and we might be able to do this, and we might be able to do it well. I'm going to close the question session. Now, there's one question more.
Well, no question, just a comment. I think both of you, what you are suggesting is totally doable. Considering this is a decade celebration, you definitely need a roadmap for a decade celebration. And I think it will enable you the opportunity to focus every year on a sub-challenge or area where you could partner with a different scientific union under the ISC umbrella. And I think ISC will be so happy to feature this initiative and encourage other scientific unions to emulate your effort.
Yeah.
I think it'll be lovely. I mean, the last presentation has inspired me to do something in the United States with all the US national committees. So I hope this beautiful, thank you so much. Congratulations. It's been a lovely event. Yes, thank you.
Thank you. I think a new topic came up, and that was sustainability built into physics. Now I'm going to close the questions, and thank you very much. We have a bus to catch. It's been wonderful to see you. The next one will be at the Hilton Hotel tomorrow afternoon, and it is a very short session with 3 critical subjects: AI, education, and nuclear threats. Thank you. See you tomorrow.